welcome to another installment of the 2021 Online Student Development Conference. I'm Mariette Harcombe, the chair of SASC, and with me today my fellow council members Joshua Kumbani, Mpumi Maringa and Kalita Shadrack. And a very special welcome to Stephanie Baker, who's going to present our lecture for today. And Kalita is our host, so I'm not going to steal any of Kalita's thunder. Kalita, over to you.
Awesome. Thank you so much, Mariette, and a huge welcome to Stephanie Baker and to any students that are watching this. Please remember to fill in the pop quiz based on this really awesome lecture. And yeah, let me introduce our guest speaker. So Stephanie Baker is the permit holder and director of research at the Dromelin Fossil Hominid Site in the Cradle of Humankind, South Africa. Stephanie is a paleoanthropologist and is a PhD candidate and researcher at the Paleo Research Institute at the University of Johannesburg. Her research interests are primarily in human evolution and understanding how our ancient ancestors navigated the African landscape. More specifically, hominid niche construction, microevolution and diet, paranthropines, and fossil carnivora. Thank you so much, Stephanie.
Thank you. Thank you so much, everyone, for having me. I'm so excited to be here today. I'm so excited to be here today, and I hope that this introduction to human evolution is a valued introduction that students can use to just give some brief overview of the complexity and the nuances within our lineage, but also to kind of hit on some of the more localized Southern African hot topics at the minute, because with most of the paleoevolutionary fields, human evolution tends to be quite a hot topic. And in recent years, we've seen a massive development in a lot of different new discoveries, techniques, and methodologies for understanding different parts of our evolutionary line. And so, yeah, I just want to touch on those, and I hope you guys find this interesting. So the first thing I want to talk about is this introductory slide. One thing that kind of drives everyone a bit crazy is seeing this wonderful linear progression line from one small, very archaic looking chimp animal up to modern humans as we see it today. I would like to here formally introduce the problem that most of those never include girls, which is a huge issue, because without us, there aren't any developments in anyone's lineage. But also the idea that it kind of dictates this very narrow, one-directional type of evolution, and that's not something that we see. So I'll speak about that in a bit more detail in a bit, but what I want you to always remember is whenever you see these are highly problematic and try and avoid them. So first things first, when you come across the literature, most people hear hominin and hominid, and these actually have very distinct meanings. And they are mostly nowadays being used almost interchangeably. But what I am going to just speak about is that these do mean very specific taxonomic differentiation. So when we talk about, say, hominins, we're actually referring to something very specific. So it comes down to Linnaean taxonomy. So if you've heard about Linnaean taxonomy, it's where we go from the class system and go all the way down. And these particular differentiations refer to the family, subfamily, and tribe level. Now, I just want to make a quick clarification that tribe means two things. When it comes to Linnaean taxonomy, it means a grouping of animals at a particular level. But in a lot of African cultural meanings, it means sorting of people based on identities. We are not referring to the latter here. What we are talking about is from a classification system, tribal level. You actually come across more regularly if you deal with buck. So bovids are often sorted into tribes, and that's one of the best examples of tribal classifications, but we're not talking about grouping of modern people. So that's something just very important to remember. So with Linnaean taxonomy, I'm not going to get into it too much, but the idea is when we talk about family level differences, the suffix that comes with that is hominidae. So ide denotes that we're talking about a large family level grouping. And in that, we are looking at all of the modern great apes. So there are the five. There's us, gorillas, chimps, orangutans, and bonobos, or what are called pygmy chimpanzees occasionally. So that hominidae is then actually referring to all fossil ancestors of all of those five groups back to what we call a last common ancestor. Whereas at the subfamily level, we start to denote it with the suffix ine. So we're looking at homininae. And that then is talking about humans, chimps, and gorillas, because those are very closely related, and all of our fossil records back to that. So now we're kicking out orangutans. We're not talking about orangutans anymore. And then all the way down to the final classification of ini, which is the tribal level classification, that is specifically talking about modern human and chimp relatives. So that goes back to at least 10 million years. We know from genetic data that that split happened between the chimp and bonobo lineage and the modern human lineage. And when we talk about hominins, we are mostly talking about that grouping. There has been a bit of a shift in nomenclature where a lot of people, when they refer to hominins, are now discrediting and not talking about the chimpanzee line anymore, even though technically speaking from a Linnaean perspective, it is still included. But most people, when saying hominins, and myself included from this point on, we will only be talking about those members of our lineage that pertain to modern human development, and we are no longer including chimpanzees and their fossil relatives. So now that that's out of the way, how does the fossil tree work? So we've come across this idea of the family tree. Everyone uses this classification. You'll see more recently, however, people are starting to refer to the braided stream. The reason for that is because the more and more time that passes and the more fossils that we pull out of the ground, the more complicated this tree becomes. And we actually know that in most cases, these are not distinct and disparate groupings. So we can have species that jot off to one side and then rejoin the tree at another point. They're not necessarily terminated with an end extinction or a modern animal representation. But the key perspective here that we need to recognize is the common ancestry. So at the base at any one fork, that one species represents a common ancestor that joins the two that diverge off of that branch or that stream. And these may later rejoin, or one terminates and they split again. But at every single node or split in that tree, those are called nodes, that is a common ancestor. And so those become quite important in modern humans and in our looking at our hominin development, because we start picking up different last common ancestors at different points, and each means something kind of different from a developmental perspective. So it becomes quite interesting. The big problem is when we talk about fossils, this is kind of what our representation looks like, right? So there's lots of gaps, lots of spots, and we have a general bias with preservation. So unfortunately, we're often trying to retrospectively fill in these gaps based on these few paltry and widely geographically disparate samples. So this becomes somewhat problematic. And that's why you see things like these trees are constantly changing, and the lines are often never developed as full straight lines. Sometimes they're dotted lines because these mean maybe, or we think so based on our current evidence. But that's the fun thing about human evolution is almost within every single find that we make, these lines change. And so it's a constantly developing and constantly changing field, which is quite interesting and also quite frustrating. So to jump into it then, what really does classify modern humans versus other apes? Now, there is a psychological debate and the philosophical debate that we can have about, you know, families and genders and being smart and coming up with all these other reasons as to why modern humans are the way modern humans are. But I'm going to speak about it specifically from a morphological perspective. And the reason why is it's what dictates how we recognize a fossil to be representative of hominins and how if it fits into our lineage and not that of the chimps, right? And so I can't talk about behavior specifically. I can infer behavior, but the fossil record doesn't preserve that kind of thing. So we can only speak about it from the morphology. So when it comes to modern humans, we know that the number one thing that we do that the other great apes don't do, at least not regularly, is we are bipedal. Bipedal means that we walk on two legs. So in order to walk on two legs, our entire body profile had to have adjusted from that last common ancestor that split off and went to the chimpanzees on one route. They remained four-legged or quadrupeds. And our lineage started that trend towards bipedality. So at different points along those various nodes in the human story, we see developments in upright walking posture. And these link to things like the foramen magnum, which is the hole at the base of the skull. In humans, it's anteriorly positioned, so it's positioned towards the face and rather not, or it's becoming away from the back of the skull, as you see in other quadrupeds. This is linked to the fact that the spine is now entering the skull almost perpendicularly or straight up, as opposed to out at an angle, right? So that's one of the first clues that we have. Linked to that, we also have things like the femur and the adjustment of the neck of the femur. So in us, we start to see this extended femoral length and a much rounder femur because it's holding a lot more weight and distributing it down. Our legs become longer and our pelvis changes shape. Our arms get shorter. And one of the main reasons our arms get shorter over time is because we're not tree dependent. And we're also not using them to walk on, so they don't need to be as proportionately long as our legs. So most things that you see walking around on four legs, the front legs and the back legs tend to be about the same length. With us, that's not the case. Our arms are much shorter relative to our legs, and we look a bit funny as a result. But it's because we're not walking on them, right? And so we also see this characteristic and quintessentially explained thing that the human pelvis becomes bowl-like, right? And that's because we're shifting our center of gravity into the midline of the body along the spine, as opposed to out the gut almost, which is what most other animals have. So you get this extension in what's called the ilium in quadrupedal animals. And as we see this progression, here's Lucy, for example, as we see the progression towards this fully bipedal-like lifestyle, you see the pelvis pulling itself in towards itself and kind of widening out front to back. So that's the bipedality, and that's kind of the first clue that we have that something that we find as a fossil is linked to us somehow. The other things that we start to pick up are mostly centered around the face, right? The crania. So the first thing is facial morphology, so prognathism versus what's called brachiognathism. So modern humans are what I would classify as the pugs of the human lineage. We have short, fat little faces, and this happens over time. If you think about something like a chimpanzee, they have a long, nice snout, much akin, if I was to continue with the dog example, like a German shepherd. They have a nice long face, and slowly over time, we see with our ancestors, this face goes shorter and shorter and shorter, and eventually slinks flat into the face. We no longer have this extended nose. We do have an actual protruding nose, but we don't have a full snout that includes the mouth, so the maxilla and the mandible. So everything kind of flattens in. With that, the shape of our jaw changes. We start to get what is called the U-shape or parabolic jaw. So if you look at the maxilla of a modern human, we have this really nice arc. It's very distinct. All our teeth become very small as a secondary result, and they cluster in. Whereas with something, say, in the middle, this is Lucy again, you're starting to see this intermediary type morphology between the very chimp-like extended rectangular face, very flattened incisor profile, down to this nice rounded edge. The other thing that comes with the teeth is our teeth, as I had said, they do reduce, they become much, much smaller, and they also become slightly more uniform in the post-canine. So we have very reduced nonsensy little incisors. Our canines in particular become hyper-reduced compared to all other great apes, regardless of whether they're herbivorous or are eating meat. So even gorillas, for example, have massive canines, even though they are fully herbivorous. And this closely links to the fact that throughout the human progression or the lineage, we start to see a reduced sexual dimorphism. And the canine and the extension of the canine tends to be a representation of heavy sexual dimorphism, where males tend to be much bigger, and there's a lot of aggression that comes with that. And so the canine becomes much smaller, and we also lose the gap between the canine and the incisors. So you can see in both the chimpanzee and to a small degree in Afarensis or Lucy, you still have what's called the canine diastema. Diastema is just a morphological term that means gap. Whereas in us, we fully have that unless something has gone slightly awry with your dentistry. You shouldn't naturally have that, right? So all of our teeth cluster nicely together, and we have this small, very nice form-fitting dental structure. This is largely to do with diet over time, and also the introduction of things like cooking, so fire, and much later utensils, right? So our teeth adapt accordingly. And then lastly, the thing that most people always refer to is cranial capacity, right? We've got nice big heads. Now, a big brain is not indicative of a smart brain, but we do see this general progression with a definite evolutionary preference for increased cranial capacity. So cranial capacity just means the volume of your head. So the brain case itself, you sometimes will also hear it being referred to as neurocranium, and that's represented with the denomination of cc. Most people think that's cranial capacity, cc, but it's not, it's cubic centimeters. So it's a volumetric measurement. Modern humans have come up into the neighborhood of 14 to 1500 cc's, whereas most modern apes are somewhere in the neighborhood of 400, so chimpanzees, for example. And we start to see within the human evolutionary tree at different nodes, this kind of constant progression. There is, of course, some wobble room in a lot of these. So things like Neanderthals, for example, actually have bigger brains on average than most modern humans today. What I would say and hazard is not necessarily of importance is the increased size capacity, but rather the increased complexity. So if you look, for example, here at the chimpanzee brain, it's not nearly as complicated and convoluted with all these dips and rivets and so on. They're called sulci. You don't see as much variability as in chimps as you do in modern humans. And that's got more to do with development of how we use our brains and language centers and all of that kind of stuff. So the more complexity in a brain, the more intelligent. A very good example of this is koalas. Koalas have actually very big brains, but they're completely smooth. Koalas are some of the stupidest animals that walk the planet, to the point where they don't even recognize if a eucalyptus leaf is not on the tree, but put on a table in front of them, they won't recognize it as food. So it's to do with the smoothness or the convolution of the brain itself. So all of that prefaces jumping into what it is we actually have on the landscape. So this is one of the nice examples of one of these trees, so to speak, and it's largely indicative of groupings. So I'm going to jump through all of these fairly quickly. I'm not going to go that deep into modern humans and the Homo genus, mostly because Southern Africa doesn't have an amazing record for it. I'm going to talk about some of these fairly quickly, and I will talk about those that pertain to South Africa specifically, because I think that's of interest here. So let's jump in with our early maybes. So there are a few that sit on this grouping that might or might not be in our lineage. These specifically are the wondrously named Sahelanthropus tchadensis, which is a brilliant name, Aurorantuganensis, and Ardipithecus cadaba. Now, the problem with these three is they are localized. They only come from three very specific sites that have very few specimens to them. So it's really hard to draw extreme conclusions about whether they are or are not definitive hominins. Sahelanthropus specifically has been quite interesting just of late, because I don't know if some of you may have seen. Recently, there was a publication that found some postcranial material that says that it may not have been bipedal. So this is coming back to those kind of key characteristics that defines hominins, and I'll talk about that in a second. The reason why I have Ardipithecus ramidus with a question mark is this one is probably, whilst it is considered an early hominin, it is probably the most likely ancestral form to the remaining ancestral species that we pick up later in the record. And I'll discuss that in a sec. So Sahelanthropus tchadensis, as I'd mentioned, it's nicknamed the Toumai Skull. It comes only from Chad, this one deposit. It's a beautifully preserved specimen, considering it is approximately 7.2 million years old. It was discovered in 2002. Most recently, unfortunately, it's despite being as important as it is and old as it is, it's largely understudied. There was the original discussion and publication of the cranium itself. Now, when you look at the cranium, what's interesting about it is you are seeing this reduced prognathism, so it is definitely fitting in that bill. And also the position of the foramen magnum is somewhat anteriorly positioned, so we are starting to look at some form of bipedality. And obviously you don't expect it to be fully anterior, because it shouldn't be 100% bipedal at this stage. We're still very early in the split between chimps and humans. And so you're starting to see some variability in bipedality, or what some researchers might refer to as tripedality, where we have extended periods of upright walking, but there still is a dominance for a quadruped style life. As I mentioned there's this most recent publication that discusses some of the postcrania that's found in the vicinity and is believed to be associated with the cranium. This has received a lot of pushback in the hominin community, as is always the case with anything anyone publishes, really. But there are some evidences to suggest in the postcrania that this was not a bipedal animal, which then does lay a lot of questions as to whether it is in fact part of the hominin lineage, or if it falls into the great hominid style fossil grouping, right? The next we're going to jump to is Ardi. So Ardipithecus ramidus was discovered by Tim White in 1994. It's nicknamed Ardi. It's a beautiful specimen, and up till very recently was one of the most complete specimens ever discovered, which is extraordinary considering it's 4.4 million years old, and comes from a non-cave-like deposit. It preserves everything from the cranium, loads of different teeth down to the toes. So it gives us an amazing reference of looking at this progression towards the modern human body profile. So we do start to see things like the introduction of this more parabolic facial structure, lack of prognathism, the upright walking. But its teeth are starting to get smaller, it's losing its gap and so on. So it is becoming a very fascinating species, and it is considered the first definitive point on the hominin lineage. So to jump into the gracils, once we've gotten the maybes out of the way, these are all definitive. So these all show clear-cut bipedality and the introduction of the modern human body profile. So when we talk about Australopithecines, this is again a Linnaean taxonomic grouping. So you'll often see gracils and robusts. I'll talk about the robusts in a bit, but it's just a way to differentiate these two groups that are characterized as definitively bipedal, but with not the modern human ratio of leg to arms. So that's usually what differentiates the Australopithecines. They're considered a more primitive grouping, because they tend to still have fairly large teeth, and the robusts are a group all on their own with crazy teeth, and we'll get to that in a sec. But this is actually a very widespread grouping. So the Australopithecines are very successful. They exist on the landscape from at least 4 and a bit all the way through to around 2 million, the last of which is sediba, which comes from South Africa. So they do persist on the landscape for a very long period of time. They are very successful. And they start to introduce, these are the guys that are pretty much introducing tools. So they're a very important grouping. I'm going to focus specifically on the South African groups, however. So everyone knows the gorgeous and adorable little tongue child, Australopithecus africanus. He's the guy that kickstarted all of this from South Africa. He was found at Taung in what is called initially the Dart deposits. Has been later reclassified as 2 different infills, but nonetheless, he dates to around about 3 to 2 million. What's fascinating about this little individual is while he is a child, he still preserves a lot of the morphology that one would expect as a definitive human ancestor. When Raymond Dart first discovered him and described him, he posited that this was what he then at the time called the missing link, which is a horrible term, but nonetheless, because of the foramen magnum is towards the front of the skull, he has a lack of a brow ridge, which one would just develop later in life, but nonetheless, it's still very unpronounced in this little individual. And he also has a much wider post-orbital constriction. So a post-orbital constriction is when you look at the cranium of something like a chimpanzee, right behind the eyes, you have this very, very pinched area before the brain case widens out again towards the back of the skull. Now, in us, we don't have that. Our eyebrows basically meet with our forehead. Our foreheads are nice and forward facing. In most other animals, it slopes back. So the tongue child is a nice example of how that transition happens, where you start to get this kind of slow gradation towards an upright frontal or forehead bone. He's got no prognathism and his teeth are nice and tiny. He does have a canine diastema, and quite a pronounced one. What is interesting is because he's a baby, one expects that to be there. So most babies actually have this, modern babies as well. It's a trend that babies often are born with these archaic-like features that as you move into adulthood are replaced by the derived characteristics that one expects for a species, right? So he's a very sweet little individual. He was largely initially thrown out as being misunderstood, and people didn't believe him for a very long time. But Africanus as a whole as a species has since been very well established. It's considered to be almost the Afarensis equivalent for Southern Africa. So it's similar like Lucy, where there is still this arboreality component to their lifestyle. Whilst they are upright walking, they still are quite tree dependent. They have the longer shoulders and the stronger shoulder blades to accommodate some form of brachiation. And they mostly are eating things like grasses, fruits. There's been a lot of work done on the dentition. Africanus we find in South Africa from Taung, Stakfontein, and Makapansgat. And the other beautifully known specimen is someone like Mrs. Ples, who is a beautifully preserved adult specimen. So they really do speak to kind of the earliest definitive hominin in Southern Africa, at least. These are the oldest that we find. The alternative to that is Prometheus. So South Africa until very recently wasn't believed to have 2 or more Australopithecines on the landscape. Most of them had always been assigned to Africanus. But the discovery of Littlefoot by Ron Clark in 1994 shows that this isn't the case, and that a lot of the Australopithecines that we find in all of these various cave systems need to be reassessed to see if we can confidently reassign them to either Prometheus or Africanus. The biggest problem with this is always sampling. With something like Africanus, for example, we don't have a very good postcranial record. And without that, it's very hard to assign things like a foot bone or a femur to any one specimen without having a reference. So Littlefoot is a phenomenal find because it is now the most complete hominin skeleton ever discovered. It has everything, at least published. And it's very well preserved. Despite the skull's a bit of deformity, it's possibly the grumpiest looking hominin in the whole world. And despite that, it is extremely well preserved, and it gives us an amazing reference for what constitutes Prometheus as a species. The biggest issue that we have with Prometheus is it comes from the Silverberg Grotto, which, like many South African cave systems, suffers from a bit of complexity. So geological complexity is what kind of drives all of the issues surrounding our dates. And so there is a possibility it is as old as possibly 4 million, or as young as 2.4. And until that's really resolved, it's going to be really difficult to kind of differentiate where it was on the landscape and how it relates to other hominins at the time. That is a conversation that is very complicated and not my place. And so until future reference, it's either 4 or 2.4, but nonetheless phenomenal. The most recently discovered Australopithecus from Southern Africa is Sediba. Actually, the most recently discovered Australopithecine ever is Karabo. This is the nickname he's been given. These are MH1 and MH2 specimens from Malapa. These were discovered recently in 2010 by Lee Berger. They're dated to 1.988. It's an extraordinary date with beautiful beautiful resolution, and one of the first indicators of how multiple dating techniques applied to these cave systems yield very, very accurate and very good dates. But what's fascinating about this particular species is because it is as complete as it is, and we have two individuals, we can start to talk about how much variability one can expect to see in a species. And it starts to make things very difficult for everybody because it's not cut and dry. And so we start to see what has since been referred to as these mosaic type features, where you have a mixing of what would be considered very derived traits or what are considered very primitive traits. An example of this would be something like if you found the pelvis. If you found the pelvis of sediba in isolation, you most likely would have designated it to Homo. But if you then see something like its leg and bone profile and arm profiles, and specifically its rib cage, it's got a very, very primitive rib cage that's more akin to that of chimpanzees. It's very wide and almost triangular, which is very unlike yours and mine, which is more barrel-like. So its ribs are Australopithecine, but its hips and everything else and its feet are very Homo. And so it becomes really fascinating because it really does represent this kind of transitional style of species that one would more expect. That shows that none of these things are temporally isolated. There is always this progression where you're mixing characteristics of those that came before and those that came after, which is why something like the braided stream analogy is a much nicer, because it's not linear and it's not temporally based. So there's more of a flow between all of these different species and taxa on the landscape. So to jump into the Australopithecines that are considered robust. So often we will also give these a separate genus names, Paranthropus. Some people will use that, some people will not. They're used fairly interchangeably, and it's largely an argument about phylogeny. So I'm not going to get into that now, but you can see things like both Australopithecus robustus or Paranthropus robustus. Personally, I'm going to stick with the Paranthropus. Simply because I prefer it as a genus level distinction, because they are behaviorally extremely different to the Australopithecines. So we can see this through their morphology. So Paranthropus robustus is what we find in Southern Africa. Most people will recognize something like Boisei or Kenyanthropus. They are these huge skulls. Now, one thing that a lot of people it's deceptive is that these are still small animals. These guys are just as small as the 1 meter tall Australopithecines that they share the landscape with. They aren't much bigger or smaller than the other Homos that they share the landscape with. But their heads are huge, which is so interesting. And it all links back almost entirely to diet. So you have this hyper-specialized dental arcade. What we start to see with the Paranthropus specimens in particular, they are so easily distinguished because of their big flat faces. They have these massive broad cheekbones that flare out under the face. And then also in the males specifically, we have what's called a sagittal crest, which runs along the top of the skull here. And it's this bony plate extrusion that is linked to feeding. So these guys are considered to have a specialized diet of very rough, fibrous foods. So not hard foods necessarily, just fibrous. So they're having to chew for extended periods of time. So coming back to my animal analogy, these guys are the cows of the human lineage. So they sit there and they just grind and grind and grind. So in order to do this, they have hyperthick enamel, and the teeth behind the canine all become very uniform. So the premolars and the molars are very similar in morphology. They become somewhat popcorny. So you see these very indistinct cusps, not the sharp kind of cusp that you would see in something like Homo, because we have a very varied diet. But all of them become these big, fat, bulbous grinding platforms, essentially. And as a result, the little ones in the front, the incisors and the canines, just become these little nubs. They become largely useless because they're not part of the feeding profile. the bony plate on the top of the cranium links to muscle structure. So when one chews, the muscles that link the lower jaw to the top of the jaw in Paranthropus extend all the way to the top of the cranium itself. And throughout that animal's life, the more they chew, the bigger those muscles get. And it forces the two bones on the top of the cranium, what are called parietals, to actually push up against one another and create this big sagittal crest. Now, this is linked to sexual dimorphism. The reason for that is because we know, thanks to the site I work at, Dreamulin, one of the specimens there that was discovered is one of the most complete Paranthropus robustus specimens found to date, DNH7. She is a female. She is significantly smaller than all other male equivalents we have on the landscape for the species, but she also lacks the sagittal crest. And so now what we know is that this is a mate selection driven feature, and it's much like something like the horns on a buck. So if you see those from a distance, the girl goes, oh, that looks very sexy. You clearly can feed yourself very well because the more you've been eating, the bigger your crest has become. So you obviously forage quite nicely. So I want you to be the dad of all my babies because you will forage for all of us. And that's basically how sexual dimorphism works. And we see it so beautifully in the paranthropines. They are very similar, I would say, as a modern analogy to something like gorillas. Whereas your Australopithecines and the earlier components of Homo are more akin to something like chimpanzees. We don't see nearly as much sexual dimorphism, and most of the mate selection is male-driven. Whereas in the paranthropines, we have more of this harem-based society with very big males. There's been some studies to show that we actually have extended growth, so they grow past their adult phase. We get secondary growth stages. So they get very, very big, whereas all the females stay quite small and they mate with just one male. So these guys are phenomenal as a species, and obviously I'm somewhat biased, but they also persist on the landscape for nearly 1 million years as a species. So not just as a genus, but Paranthropus robustus, as we recognize it, is in Southern Africa from as early as 2.1, 2.2, depending on which site you're working at, all the way through to 1 million years. So the most recent dates that have just come out of Swartkrans, which I'll chat about in a bit, actually suggest that they have the earliest Paranthropus robustus, which is amazing. So at 2.2 million years old, we know that these guys are walking the landscape. And they actually share the landscape with the last remnants of Australopithecus in Southern Africa. So examples like sediba, but also the first introduction of Homo. And that becomes really important because the landscape shifts quite dramatically over this time at the 2 million mark, from a very forested type environment to a more open grassland like we see in Southern Africa today. And these guys are living throughout that transition, and they navigate it quite well, despite being ultimately in possible competition with something as adaptable as Homo. So it's quite a fascinating species for me. They are loosely associated with bone tools, although I would hazard that there's no reason to assign bone tools specifically to Paranthropus robustus, simply because bone tools have been found with multiple other species. And also most of the stone tool assemblages that we have in South Africa, funnily enough, are also associated with Paranthropus robustus and very little Homo, despite stone tools being associated with Homo almost in isolation. So there's some things to consider. They have fairly large brains, akin to most of the other species on the landscape at the same time, and their hands were just as adept. So there's a lot of work that needs to go into something like Paranthropus. They have been largely overlooked, despite having a much better fossil sample than any other species in the Southern African record. So yes, I'm very biased, clearly, but I think they're absolutely fascinating. To come into it though, we have to speak about Homo. Homo is all over the place. There are so many different species. After around the 2 million mark, when we get the introduction of some of the earliest evidence of Homo in both East and Southern Africa, it radiates completely. And it's specifically down and thanks to Homo erectus, who pretty much leaves Africa and populates everywhere else in the world, and Homo goes nuts. And what really qualifies Homo as a genus and what makes it so fascinating is the adaptability. And that's something that we've not seen in any of the other taxa up until this point. everything else becomes hyper specialized to a very specific type of environment or a very specific type of habitat or diet. Homo doesn't do this. Homo is able to move to a new landscape and use it just as well and apply things it has learned prior to this new habitat. And that's what makes them phenomenal at occupying varying landscapes and also just populating the world, essentially. So from Southern African perspective, I will talk about some of the earliest Homo that we have here, but it is worth mentioning that we have some of the earliest DNA evidence for Homo sapiens from South Africa. So we do know that something like Homo sapien and the genetic identity of Homo sapien is Southern African, which is very exciting. But we also have new fun finds like Homo naledi, which are still being developed and still being understood, which date to far more recently. And they occupy the landscape at the same time as other Middle Stone Age individuals at around 350,000 and onwards. So it becomes quite interesting. I'm not going to get into that mess. And the reason for it is because it is chaos. The Homo explosion is very difficult to understand, and there's a lot of nuance and a lot of geographic variability. So we focus in just on the Pleistocene level Homo record of Southern Africa. The first guy we have to speak about is Homo erectus. And what's fun about this is until last year, this wasn't something we would have discussed. So I was very fortunate to have been part of the team that discovered the Homo erectus specimens from Southern Africa, from Drumulin. His nickname is Simon. He's formally named DNH 134, and he is dated to 2.04 to 1.95 million years old, which is phenomenal because not only is he the oldest Homo erectus in the world, but also the first evidence of Homo erectus in South Africa. Which is great because until very, very recently, he was also the oldest by quite a long margin and geographically. So the next in line temporally would have been the Dmanisi specimens, which date to around 1.8 million. And this really does then speak to this testament that in 200,000 years, we have what we recognize as Homo erectus and not Homo ergaster. We made a very clear argument that this is Erectus sensu stricto. So it includes ergaster type morphs. It moved from Southern Africa all the way up and left Africa and found itself in Georgia, which is near Russia in Europe, at 1.8 million. So in 200,000 years. So the only way one's going to do that as a taxon is adaptability. And the amazing ability to transition from African grasslands to African deserts, to African forests, all the way up into what essentially are frosted permafrosts and tundras. So this is an extraordinary species. The problem with it is that it's very, very complicated. Homo erectus, technically speaking, persists for 2 million years. Now, what one needs to consider then is so much has changed and we have a lot of geographic variability. So it starts to become quite complicated when one considers, well, how much variability are we willing to accept in a species, because we can have Southern African style Homo erectus, East African style Homo erectus, European, all the way through to Asian. So some of the specimens from Trinidad and Trinil in Indonesia. So there's a lot of variability, a lot of temporal variability, but also a lot of behavioral variability. So this is something that I think is going to be a very hot topic in paleoanthropology for a number of years to come, is trying to tease out the amount of kind of delineation within this particular taxon. But what's really important about it really, and what classifies it almost entirely to Homo erectus, is the fact that we have this expanded brain case. We also have this pinching under the brain case. This is one thing that's quite important, is this posterior, what's called the orbital. So with this, it starts to kind of link under, and we get this bowl shape, which you and I share today in the back of our craniums. And that becomes quite important. And we see this in the earliest members of Homo erectus. So that's quite a nice thing. These guys are definitively upright walking. There is no question about it. They have very human-like proportions with much shorter arms relative to much longer legs. And we even see things like Nariakatomi boy from East Africa. He's very tall and surprisingly tall. I mean, he's taller than me. So he's extremely tall for his being as young as he is. So we're not entirely sure, because he is a one-off beautifully preserved specimen. Again, it comes down to this fossil record sample. We don't know if that's true for the rest of the sample and the species as a whole, or if he is a weird outlier, but they do definitely start to have this more elongate upright posture, long walking strides, and a much bigger brain case. You also start to see that post-orbit constriction, or that pinching behind the eyes, is almost entirely gone now. So we're moving quite rapidly into a more modern human style face and walking posture. We have to talk about Homo habilis, or otherwise nicknamed the Handyman. So initially, when discovered, he was the guy linked to stone tools. Now, the problem with Homo habilis is he's maybe found in Southern Africa. South Africa, our Homo habilis samples from Sterkfontein and Swartkrans are one specimen each. One of them is the one that you see in the picture here. The problem is because it's just the one each, we don't really know. There's been a lot of debate. The one that you see in particular has actually been secondarily reassigned to Australopithecus by some researchers, and then reverted back to Homo habilis by others. And then Swartkrans might have habilis specimens, but again, these are heavily debated. What you will typically see, though, for Southern African record of Homo is pretty much everyone refers to the Homo samples that they find as being either Homo spa or just simply early Homo, because there's a lot of variability. And the sample, unfortunately and bizarrely for Homo, is very small. Quite paltry, it's poorly representative, it's mostly isolated teeth, and so it's difficult to draw very distinct conclusions about where they fall within all the variant taxa, because like I said, there are so many to choose from Homo, so it's safer for everyone to just go early Homo, because we know they're definitively not Paranthropus, and they're also not Australopithecine, so there's somewhere in that mix. The other problem is that Twiggy, which is another East African specimen, OH24, is beautifully preserved. And that really forms the basis of what constitutes as habilis-like morphology. It's an East African variant, and so we can't expect the South African equivalents to have the same morphology because they're living on a different landscape. So whilst they will be similar, there will be regional variabilities. And so it becomes quite difficult for us with our smaller sample that is a less more fragmentary to then kind of exactly pinpoint it to accommodate for regional changes. So unfortunately, there's not much to say about Homo habilis other than we might have it in South Africa. And then finally, just to finish off, to talk about some of the very exciting new stuff that's happened. I have touched a little bit on some of the Paranthropus robustus and Homo erectus finds that we've had at Drumuland, but as a field as a whole in Southern Africa and in the world over, paleoanthropology, and particularly in this Pleistocene period, has just boomed in the last 5 years. Developments in dating techniques, our understanding of geometric morphometrics, neurocranial scanning and CT scanning, and being able to change the shape of the brains and understand what was developing when, all of this has become massively important, because we just see paper after paper after paper that just changes up the story. So you always see the wondrous tag clickbait of we've changed the human story once again. Well, I mean, in a lot of ways, this is true. And we are constantly changing the story of human evolution. And that's what's nice about science, is it's never a stagnated thing, and things change. And with this rapid pace of technological advancement, but also the fact that we have been doing this for over 100 years now, and the sample has developed to the point where we are finding so much more that we're starting to close some of those gaps in the tree that I showed you. And so just to touch on some of the more recent ones, the new find from Homo erectus, the cubiform material. So the find itself was actually made many years ago, but some people have been able to date it. In particular, Salindo was on that paper, which is very exciting. I'm not sure if you probably all have heard of Salindo, if not met him. And he's done some amazing work being able to refine the fact that that material dates to at least 1.855 and is probably older, which is extraordinary because it really does confirm this Africanized origin point for erectus and then the later expansion into Europe, which is just phenomenal. And it's an amazing resolution that we could only have dreamed of 10 years ago. Also, I mentioned as well, Swartkrantz Lower Bank has just published dates, cosmogenic nuclide dates, that say that the deposit is 2.2 to plus minus 0.08 million years, which is great because not only does this mean that Paranthropus robustus moves back in time, albeit their Paranthropus robustus sample is extremely low and largely made up of fragmentary teeth. It doesn't matter. It's associated with one of the largest collections of older one-stone tools in Southern Africa. And so we can now put that at 2.22, which makes it the oldest tools, and it makes it a really, really important date overall. And then finally, microevolution in Paranthropus robustus. So coming back to my wonderful bias, we recently were able to publish, having discovered 2 brand new Paranthropus robustus skulls from Dreamulin. We discovered a big individual named DNH155. And he is gorgeous. He now takes the cake as the most complete Paranthropus robustus cranium ever discovered. But because he is discovered alongside DNH7, which is the female Paranthropus that I had spoken to you about earlier, but also another individual from Dreamulin called 152, who is also very well preserved. All 3 of these interestingly show morphological population level similarities to one another that they do not share with other well-preserved crania from either Swartkrantz or Krumdraai. And what was interesting is prior to the discovery of the 2 male crania, the differences that we saw in DNH7 relative to things like SK48 from Swartkrantz and some of the Krumdraai material, those were explained as being sexually dimorphic differences because she was smaller, she's a girl, she looks a bit weird. Well, it turns out that that's not the case. All the boys from Dreamulin look a bit weird too. But what we've been able to do is, coupled with the amazing dating resolution that we have at Dreamulin, relative to that of the other sites, we know that Dreamulin is at least 200,000 approximately years older than Swartkrantz, for example. Specifically the hanging remnant, which is where all the other large crania for Paranthropus come from. And so what we've suggested is that this is representative of population level change in a species, which is a resolution in change that we haven't been able to pick up in many years. And it's something that we hope we'll be able to start applying to things like Homo erectus, because we should be seeing small micro changes within a population over very small periods of time that lead to much larger scale changes and specifically potentially species level changes over longer periods of time. So this was a really exciting paper to have worked on. And we think that it's mostly driven by climate. So remember I spoke about how Paranthropus robustus have that very distinct dietary adaptations. Well, most of those actually weren't in place in the Dreamulin sample, which represents one of the earliest samples for the species, whereas they become very determined and characteristic of the species in the later populations. So we are saying that those changes in the environment over the time pushed the change towards the morphological features in the face to accommodate for diet. And they did this very rapidly, which is a very cool thing to have been able to show in fossils that are 2 million years old. So I hope you guys enjoyed that. I know it was a fast-paced introduction to the world of human evolution, but that is 7 million years worth of data to get in. And yes, I hope you guys have great questions.
Thank you so much, Steph. That was incredible. I think a lot of the students watching are blown away just at how far our fossil record actually goes in Southern Africa.
Yes.
I think it's a beautiful record. I'm also biased, however. And congratulations on all the awesome studies you've been pumping out, by the way. It's
Thank
amazing. Breaking that glass ceiling, I like it. So I'm just going to invite the other council members to ask you their questions first. If someone wants to go shotgun. Mariette?
I'll go first. I'll break the ice. We're breaking a lot of stuff, breaking glass ceilings, breaking ice.
Hopefully not breaking fossils.
No, please
No.
don't. So Stephanie, if you had to give some advice to students in terms of fields of specialization, like are there any like subdisciplines or fields of specialization that would make kind of like really good crossover or complementary fields of study to paleoanthropology?
That's a great question, and it's something that I grapple with often. What I find nowadays is a lot of students are hyper specializing in any one area. And I would somewhat hazard against this. The reason why is because you kind of niche yourself out and you make yourself unhireable. Because at the end of the day, whilst the science is very exciting, jobs are really where it's at, right? And we need to be able to train students who are going to find jobs. And so what I would highly recommend, particularly within paleoanthropology, is developing a technique. So becoming methodological based rather than subject based. And what I basically mean by that is don't become a specialist in the upper left canine of Homo ergaster. You know, and then you can only work at sites that have the upper left canine of Homo ergaster, and you have no applicability elsewhere. What I would, however, suggest is rather specialize in something like geometric morphometrics or in understanding CT scanning technology and neural cranial development, or the understanding how foot bones differ between various individuals. And in all of these applications, the subject matter is almost irrelevant. You can go to any site, regardless of their sample, and apply your techniques. That would be my biggest thing, because you also don't want to just hyper specialize yourself into Southern Africa. You want to be able to expand and go and work in East Africa, or even go and work with Neanderthals. If you understand how to scan a face and use the data from those scans to develop inferences about diet or body proportions or whatever the case may be, then it doesn't matter how old or what the species is or where in the world you are, you can use that technique. But even then, it doesn't even matter if it's hominins. You can do it to primates, you can do it to carnivores. So rather become specialized in an application rather than a very specific subject matter. Like, I understand that we all have our interests, and we all want to know, you know, because this is an interest-driven field, right? None of us got into this because we want to make money. We all got into this because we like fossils and weird old things, right? And so, you know, rather focus that for your immediate, for your subject matter, but make sure that the methodology that you're using to explore that gives you a lot of avenues and paths outside of both South Africa and possibly out of academia as well.
Oh, thanks for that. I think that's a really great recommendation. Thanks.
Thank you.
Definitely, and I think our students will really enjoy that advice. Josh, do you want to ask a question? Because I see you've unmuted yourself.
Yeah, so I have one question for Stefan. Thank you very much, Stefan, for a good presentation. I've realized that in terms of hominid remains, it seems as if they are mostly from South Africa, and then we go to East Africa. I wanted to ask, is it because of preservation conditions that allow for the preservation of fossils in these areas, or the reason why we do not have evidence from other regions in Africa? Is it because of preservation conditions or because of research bias that people they only concentrate on East Africa and South Africa to be specific?
All right, that's a great question. I think people may have struggled to hear that, but essentially the question, if I'm right, is why do we see this kind of localized preservation in Southern Africa and then Eastern Africa of these early Pleistocene, these specimens? And is it a preservation bias or is there another reason? Is that right?
Yeah, exactly.
Okay. So yeah, no, it's a great question. It's one we're asked often. And it's one that makes understanding the whole fossil hominin record quite tricky. These are not the only two places that we find species and specimens necessarily. It is a preservation bias. And it's not to say that these things occurred in isolation, so that there were only little hominins walking around about 40 minutes north of where Johannesburg is now, and then walking around Lake Turkana, and nothing in between. That's definitely not the case. They were all over the place, but because of the geological requirements and the very, very specific types of chemistry that we need in the soil to preserve fossils is why we end up with this record that's kind of patchy. So the cradle of humankind, for example, it's actually a geological demarcated area. It's what's called the Transvaal supergroup. It's a dolomitic outcrop. So it's the Malmanis specifically. So these dolomites and these cave systems, because of their high lime component, preserve fossils. So anything that falls into them, they create these kind of catchments, and the lime moves through the system. It takes out the organics in the bone, and the fossil diagenesis takes place, and we end up with the fossils themselves. But that's not to say that if someone was walking around in the landscape 3 million years ago and then died in the middle of the desert, they were there, but the fossils don't remain. So unfortunately, we have to kind of create the mental jump that all of this occurred in uniform, but we only pick up these two isolated kind of disparate areas. East Africa is somewhat different. They don't have the cave systems. Those are open landscapes, but they are interbedded with these volcanic kind of ash layers, and that's again what leads to the fossilization taking place there. A really good example of this is something like chimpanzees, right? So we now have chimpanzees in one very specific little area in the world, but that wasn't the case millions of years ago, and we know that from their genetic evidence that they first come into kind of play and split from our lineage of the Homo line of hominins around 10 million years ago, give or take. But there is, I think, in the world, all of 5 chimp fossils, right? And it's because chimpanzees developed and evolved in an area with forests, and it's far too moist and it's far too wet, and so the bones just don't remain. There is, however, been some progression with some Western African areas, because the dolomites that we talk about in South Africa, they occur there too. They're in areas like the Congo, though, and DRC and things like that. And unfortunately, those places don't really lend themselves to academic research at the minute. But there has been some talk of exploring those areas. So there are places where we might pick up more of this kind of sub-Saharan African human evolutionary story, but they haven't really been explored as much. But yeah, it largely does come to the fact that there is this distinct geological-driven preservation bias, and why we only preserve things in very specific areas of the world.
Thank you.
Thank you so much. Thanks for the question, Josh. I see Enio has joined. Hi, Enio.
Hi, good morning.
Hi. Hi, Enio is also a council member. So Enio, do you have any questions for Stephanie?
I don't have any question because I joined recently and then I didn't follow the presentation.
Okay, no problem. Mpumi, would you like to ask a question?
Yes, thank you so much, Kalita. Thank you so much, Stephanie, for your presentation. It was very informative and it touched bases, even though you went through it quite briefly, but I felt like I went with your understanding. So my question is based on because you spoke a lot about the dentition of the fossils, I just wanted to know, what are the dietary changes, if there are any, that resulted in an increase in cognitive complexity throughout the human evolution?
Ooh, what a phenomenal question. Okay, that's great. I love this question a lot. So yes, absolutely. So teeth are phenomenal. Just to kind of cycle back somewhat. Why we love teeth as much as we do as paleoanthropologists is because they practically are fossils already, right? Your teeth have a very similar chemical makeup to a fossil bone. They are basically rocks, all right? So your little face rocks preserved in the fossil record brilliantly. And so they're one of the most commonly found items in the fossil record. And so they give us a lot of insight because there are as many as there are, and they're as preserved as well as they are. They provide us a lot of information, and you can use them in multiple ways. So not only is the morphology of a tooth indicative of the type of diet that an animal has, but we can also use things like isotopes, which tell us the composition of C4 or C3 type foods or oxygen levels. And so that tells us, are they eating plant-based materials? Are they eating meat? So we can tease that out. We can also look at things like microwear and microabrasion, which is this high-powered microscopic superficial look at the tooth to look at pitting and scratching, which then tells us, they were eating things that had high pit constructions to them, so they were quite fibrous like fruits, or they were eating more grainy, gritty things that left striations. So we can start to build up diets quite nicely with teeth. And then we can couple that, back to diet, which then drives kind of this increase in cranial capacity. The number one thing that almost everyone speaks to with what kind of catapulted this massive brain was the introduction of meat to our diet. Now I'm going to hamper that with, there's pretty much no evidence to suggest that meat was never part of our diet, right? If we look at modern chimpanzees today, meat is a very critical component of their diet. The problem is understanding when we started increasing that kind of meat component, because most of the meat that is included in the ape diets, and this is specifically in Pan because gorillas and orangutans don't really eat meat at all, but in Pan, so the bonobos and the chimpanzees, it's largely opportunistic. So you're coming across a carcass and you're going, oh great, okay, I'll chew some of that off. Or every now and again they will go out and they'll hunt things like red colobus monkeys, but it's a very small component of a much larger dietary kind of adaptation. What we start to see specifically with things like Homo is we start to introduce cut marks into bones. So this is great evidence for the fact that we're purposefully prioritizing butchering and sourcing meat. So it's no longer necessarily just opportunistic. We are going out and foraging and finding these carcasses on the landscape, and we are taking stone tools with us so that we can cut as much of this meat off the carcass as possible, not just using our shearing teeth anymore. So that shearing component of our teeth starts to fall away, and because we're replacing it with sharp tools, right? And then we start smashing the bones open and so on and so forth. And what really kind of builds to this is the caloric intake, so the amount of calories that one gets from eating flesh. So when we eat meat, we get a huge amount of calories. It's a massive boost, and particularly things like fat. Fat is a brilliant thing to eat if you plan on running a marathon sometime soon, right? Not regularly, you will die. Please don't eat fat all the time. But for the most part, if you are looking to gain as many calories as you can, fat's where it's at, right? Fat, brain matter, tongue, big muscly things, right? So when we start to introduce all of that into our diet, and we start introducing it well, and that's when we're introducing things like stone tools, but also sociability, we become aggressive scavengers. Because we create these kind of social groupings, we become more aggressive and more of a challenging scavenger, as opposed to, think about one isolated little 1 meter tall hominin on the landscape against a saber-toothed cat who's just killed something. you're going to be dessert. You're not scaring nobody off of this meal, right? But if there's a group of you and you're throwing rocks and sticks and screaming, and you become quite a scary grouping. So this introduction of sociability couples in with this introduction of meat, because we can scare carnivores off of a carcass much earlier in their feeding process, and we then retain as much of the carcass as possible, right? And we're able to feed much earlier. So when you start introducing these caloric intakes, we see this meteoric rise in cranial capacity, because we're still including all the other aspects of our diet that sustain us calorie-wise, and all of that excess calorie intake can be then diverted to creating our big brains and running them. Because having a big brain is one thing, but eating enough to sustain it is another. And so we have to adapt that kind of behavior to allow for this constant intake of high calorie foods. Your vegetation-based diet is not going to get you there. The amount of calories that one gets from a huge salad versus just a steak are massively different, right? And everyone knows this, and this is why we all have to diet as much as we do. But it's essentially based down to that. It's like being able to eat less, but get more out of it in the long run. Right. And so, yeah, you definitely see the intake of meat being a number one indicator. And weirdly, with the teeth, it does couple in a way. So we know from an isotopic perspective that we're starting to introduce a lot more proteins with Homo specifically. And we also obviously see the other evidence for cut mark, but our teeth don't adapt to eating meat. Weirdly, they go the other way. Our teeth adapt to becoming kind of more generalist and useless. We don't have meat-eating teeth like one would expect, like carnassials, even though we are increasing the meat. We've lost that capability, but we've replaced it with externally derived abilities like making stone tools. And then later with the processing, because we start to lose the strength in our jaw to then eat raw meat, we start cooking the meat. And so it's all kind of linked together, that our teeth do almost the opposite of what our diet suggests, because we as Homo are so adaptable that we change the environment around us rather than changing us. And that's really what a very Homo-like characteristic. I hope that made sense.
Wow. Mpumi, are you satisfied with that amazing answer?
I am. I feel so educated now.
Awesome.
Thank you so much, Stephanie.
You're welcome.
I just want to ask one question, and I think it's just it's a very simple question, but I think it might be very important for students who are not so familiar with archaeology or archaeology in general, especially if they're still beginning their careers. What would you say is the appropriate procedure to follow if one does come across what seems to be fossils or artifacts in public areas, pretty much, or on the landscape?
Yeah, that's a great question, and it happens more regularly than one would think, particularly with things like archaeology. Archaeology tends to be scattered all over the place. Anywhere around Joburg, if you're somewhere near the Vaal or any of the river tributaries, there tends to be some archaeological things. What I'd highly recommend is not picking things up. As a general rule, if we don't know where it comes from in a site, we've largely lost its context. So that makes life difficult. What I would, however, say is that almost everyone at every point in time has their cell phone on them, right? It's now, like I said, with Homo, everything's become externalized, and cell phone is an extension of us. And so we use this technology, and you can use it to take photos of what you found, where it is. Always include something familiar like a scale, that like coins, because we know how big coins are, they're standardized. Do not use your credit card. Somebody has done this before. It was one of my favorite things. A lady sent me a photo of a skeleton with her credit card for scale, and in the next photo it had been flipped over. So I could have robbed her. She's very but yeah, so use something like a coin or a pen, something that everybody has and we can familiarize ourselves with size-wise. And then take GPS coordinates, save the point, and then email somebody. So pretty much anyone working in the field has a media profile or is linked to an institution. Email them and we can then take it from there. We'll contact you, you can take us out, or we'll go out on our own with the GPS coordinates that you've sent, and we'll either collect it or we'll leave it there, because sometimes it's not worth removing it. We need to kind of think about the idea that paleoanthropology and archaeology and excavation are destructive. And if we remove everything, we can never put it back. So we have to be quite ethical about whether we are going to take things away or if we really need to, because this is everyone's history, and maybe 20 years from now, somebody needs that material to be where it was. And so, yeah, so always take a photo and then GPS coordinates and email or call.
Awesome. Thank you so much. And again, thank you for giving us your precious time, because I know you are working very hard all the time. And thank you to the council members for joining. And I think Mariette's going to end this off as per usual. I'm stealing her job. I apologize.
As is tradition, and I'm a non-traditionalist. I don't mind stealing some of the thunder. But yes, thank you very much, Stephanie, once again from us as council. Thank you very much for contributing to this online conference. And Kalita did mention this earlier, but to the students tuning in, please remember to go and complete the questionnaire associated with this talk. That's one for the blooper reel, by the way. And yes, look out for the remaining content. Still some exciting lectures coming up in this conference series. Once again, thank you everyone for joining us, and have a good day further. Bye.
Thank you.